everyone. Welcome to another episode of AI Research Today. I'm your host, Aaron from Architect AI, and yet again, today we'll choose another paper that I found particularly interesting that was a recent release to go through in depth. And the paper that I've chosen today is called Learning to Reason in 13 Parameters. So this was a paper released by Meta on February 4th, so just a couple weeks ago. And the paper itself focuses on ways that we can more efficiently fine-tune a language model. So there are a lot of different variations of parameter-efficient fine-tuning techniques, most notably LoRA or low-rank adaptation. And we'll talk a little bit about LoRA, some of the research and their contribution here. So there are a few different ways to fine-tune a language model. Full fine-tuning is the most heavy version of this, where you're performing gradient updates on all of the weights of the model. And you can do this using reinforcement learning, or you can do a full rank update using supervised fine-tuning methods. Either way, doing a full parameter update obviously requires a lot of compute. And so the question becomes, do we need all this compute to fine-tune the model for this task that we're trying to get it to learn how to do? Or is there some subset of parameters of the model we should actually be focused on that actually contribute to this task? So obviously the answer is yes, and that's where LoRA came from initially. So LoRA itself is, if you can imagine the weight matrix of a deep learning network, denote that as W. You can decompose this dimensionally by constructing matrices A and B, where the rank of these A and B matrices are of some dimension that you choose. Let's say dimension R. So if your W matrix was D by K, let's say, then A would be a D by R and B would be R by K. So when you multiply A by B, you recover the original dimensions of the W network. And LoRA is typically done using, at least the traditional LoRA is using a random initialization of the weight matrices A and B. And then you perform fine-tuning by updating gradients or updating parameters of these submatrices A and B. And since A and B are of smaller dimension, it requires smaller GPU footprint. And so you can reduce the amount of compute being used while still getting some benefits of fine-tuning on a data set. So that's kind of the traditional approach that LoRA takes. I mentioned you have to choose R, which is like the rank of your update. So the larger your R is, the closer to a full rank update that this is. So, a full rank would just be like updating the initial weight matrix itself. And so you can choose smaller ranks of these decomposed matrices to take up smaller footprint, but the trade-off is your performance could be worse as your R shrinks. So there's been a lot of research into how can we target or reduce the number of parameters that we're updating on our model while still retaining performance increases. And there are a few different ways that you can, like I mentioned, update your model: reinforcement learning or supervised fine-tuning. And you could do RL on a low rank decomposition as well as supervised fine-tuning. You're just changing your objective from cross-entropy loss with supervised fine-tuning into reward maximization with reinforcement learning. They come up with these interesting plots in the beginning of the paper. So the paper focuses on the Quinn model family, which is a pretty impressive little model family out of Alibaba. They just released Quinn 3. This paper is done on Quinn 2.5, I assume because they started the research before 3 was released. But Quinn 2.5 is a 7B model, and they are looking at performance on GSM 8K, which is the grade school math set of challenge problems. So you basically want to tune your model to be good at these grade school math problems. And they show charts comparing GRPO versus supervised fine-tuning for these low-rank updates. And what's interesting is that they show that with reinforcement learning, the size of the update you need to achieve kind of asymptotic performance limits is much smaller than that of supervised fine-tuning. So they have kind of a log plot from 10 to millions of parameters for these LoRA decompositions, and then they compare like what does our performance on this GSMK look like as we increase parameter size using either reinforcement learning or supervised fine-tuning. So for reinforcement learning, within 100 or 1,000 parameters, they're sort of reaching the asymptotic limit of this model's performance on the GSM 8K benchmark. Whereas for supervised fine-tuning, it takes up to the 10 to the 7 around to get those comparable performance gains. And they have a discussion around why they speculate that this is the case. There's not a theoretical justification for it necessarily, but the difference is in the objectives. So when you're tuning a model, let's say you provide it with some example. In supervised fine-tuning, there's no reward. You just have a single output. These are just assumed to have been sampled from a perfect reward distribution. So you have an input and some expert output, and you're updating your model on all of the tokens and the output of this example. And there are potentially a lot of noisy tokens that aren't necessarily directly associated with what is considered to be a good response. And so in order to capture the full breadth of the quality of this example, you have to propagate a lot more information back up through your model. Whereas reinforcement learning is solely using the reward signal itself and whatever, parameters you're trying to tune. And so there's less information to propagate upstream to the model. So the individual tokens, which could be noise, are contributing less noise to the updates in RL versus SFT. So this insight is what leads them to propose this TinyLoRA, what they call TinyLoRA update method, where they say, okay, if RL is much more efficient than SFT at propagating critical updates through the model, and is able to do it with a smaller parameter size, maybe there's some way we can reformulate the LoRA technique to take advantage of this insight from RL. And so that's really the core hypothesis of the paper. The related work they discuss is fairly run-of-the-mill, so I won't go through it. They talk about fine-tuning. There's obviously a million variants of LoRA. There's other research into how many examples we need to do a sufficient SFT or RL. There's some Pareto frontier of number of examples the model might need. And then there's additional work comparing SFT to RL, which they leverage in their initial comparisons. Okay, so the update capacity for supervised fine tuning versus reinforcement learning. That's what I just mentioned. That's another section of their paper here. So they call out, and I'll just rehash again. They call out the difference in objectives, where for a policy gradient reinforcement learning, you're really doing this log likelihood ratio of continuations given some reward function. So you're optimizing to maximize your parameters theta in order to maximize your reward. Whereas for SFT, your objective function is just the typical cross entropy loss for tokens generated. They do call out that RL generates more information. So you when doing an RL tune, you generally produce several rollouts, as they're called. So you might start with some initial prompt X, generate several example outputs, score those with a reward, and then perform your gradient updates. So there's a lot more information, so potentially more noise. But the relevant information of the objective lies entirely in the reward, which is how their point here is that their RL method may generate more noisy data, but really the part that the objective is paying attention to is the reward function as opposed to the actual generated tokens being optimized. And so while it's producing more data, it's more efficient with that data than SFT is. So, okay. I just had to get some coffee there. Okay, so TinyLoRA, what is it? What's their technique? So they talk about traditional LoRA. So if we take some weight matrix, we'll call it W prime, and decompose that as a sum of W and A times B, where W prime is our tuned or optimized weight matrix, W is our initial weight matrix, and A and B are our LoRA decomposed matrices. So A and B, given that W is a D by K matrix, A would be a D by R, and B would be R by K dimension. So when we multiply A and B together, we recover the full D by K dimensionality of the initial weight matrix W. But tuning A and B separately requires a smaller memory footprint. But there are potentially still a lot of parameters to be optimized with LoRa, because we can apply LoRa. I mentioned W. How many W's are there in a transformer architecture? A lot, right? You could have W's for the attention layers, the projection layers, the MLP layers. So there's a lot of different modules you can apply these adaptations to. And if anyone's done a LoRa fine-tune themselves, they'll know that you, like in the Hugging Face API, have to specify the parameter or the layers within the model that you want to perform LoRa on. And so there's even like an additional hyperparameter of where, not only the dimension of the LoRa, but where you're going to actually perform the LoRa throughout the model's architecture. So one thing they do next that I find interesting, so I'll give a fish that got away story here. We had actually started a research group I'm involved in had started doing a research project where we were investigating LoRa and if we could improve LoRa by using singular value decompositions. Because as I mentioned earlier, the weight matrices being tuned in LoRa are traditionally randomly initialized. And so it's sort of like a poor man's singular value decomposition. So what if instead we decompose W into this SVD framework and then tune the top principal components of this decomposed version of W? So we had actually just started a research project on that. And then another group released a paper doing the exact same thing. So LoRa variants using SVD for initialization and targeted tuning. Which just kind of comes with the territory of AI. It's a very rapidly moving space. So as soon as you have an idea, you better get it out quick because someone else has had the ideas almost certainly. So they do something similar here with an SVD on LoRA. So they take W and they perform a singular value decomposition on it. So you get U, sigma, and V, which are your left and right singular vectors, and then sigma representing your singular values. So you sort of, the analogy would be a vector comes into W, it's transformed into the V basis, scaled by some directions in sigma, and then output in the U basis. And so if we can only choose the top singular vectors by magnitude of their associated singular values, we can capture the largest amount of information in our update while, keeping the amount of memory footprint needed to perform the update as minimal as possible. So their suggestion is, when doing this update, what we're gonna do with TinyLoRA is we're gonna perform a singular value decomposition on W. So we get U, sigma, and V, our left-right singular vectors and values, and then we're going to construct a set of N randomized matrices. Okay, so let's table the SVD for a minute. And let's go over here. And now we're going to generate, let's say, 3, 4, 5, whatever randomly initialized matrices. These could be sampled from some multivariate Gaussian distribution. But within the subspace of the singular value decomposition, each of these randomly sampled matrices are going to represent some random direction in the subspace of this decomposition. So we have, they call them P matrices here. So we sample P matrices. They're, again, randomly sampled from some distribution. They represent some random direction in this targeted subspace. And we're going to multiply each of those randomly initialized matrices by some scalar value. Again, this could be randomly initialized as well. And so what we're going to do is we are going to tune these scalar values, and we're going to sandwich the sum of the multiplication of these scalar values and the randomized matrices. So for each of these randomized matrices, we have an associated scalar value. Let's sum all those together. We get some quantity, and we're going to put that back into the SVD. And that is the quantity that we're going to tune on our task when fine-tuning the model. So now in original LoRA, our tune matrix W prime is equal to W plus A times B. In an SVD version, the tune matrix W prime is equal to W plus U sigma, part of the SVD, times the sum over these randomly initialized matrices times the right singular vectors. So why does this work? Okay, so the benefit is that now we're only tuning a vector of scalar values. So let's say that we take three randomly initialized matrices. So those are going to tune towards the subspace represented by the top three singular vectors due to the multiplication of all these quantities together. And we're going to allow these scalar coefficients to shrink and expand and change magnitude in order to take these randomly initialized vector directions and kind of squeeze them into the direction of the update we ideally want that's associated with the SVD. So if you think about it like a room, so imagine that the direction that we want to update is somewhere along the floor, 2D plane. And let's say that we have a bunch of flashlights, which represent these randomly initialized P matrices, and we kind of shine them in random directions throughout the room. The hypothesis is that if we sum all of these flashlight beams together times some scalar, then we can recreate the ideal vector that's actually on the floor. So basically that in a high dimensional vector space, these randomly chosen vectors are almost guaranteed to overlap the ideal vector, the ideal update that we want for our model. And the benefit here is that you're now just tuning a vector of scalars. So you're tuning maybe 10 parameters per weight matrix. And they also mentioned that you can do weight tying as well. So you can share weights across layers rather than having unique weights or scalar vectors for individual layers. And this allows you to further reduce the number of things that you're tuning. And they get down to tuning just single parameters. And that's where the title of the paper comes, Tuning LoRA and 13 Parameters. The reason that this works and is because of the comparison they make early in the paper with reinforcement learning versus SFT. Reinforcement learning is able to extract information more efficiently, disregarding generated noise. And so by combining this singular value decomposition approach with reinforcement learning, specifically GRPO, during their training algorithm, they show that they're able to achieve comparable performance to larger update cycles, which is a pretty cool result. So they compare this on the Quinn model series, Quinn 2.537, 7B Instruct, and 7B Math. And they show that their technique is able to achieve comparable performance using GRPO as some larger LoRA updates would achieve. They have some additional graphs around rollouts and kind of reward over time, which I won't try and describe specifically. But that's the core gist of the paper. So comparing a full fine tune to a LoRA to different LoRA variants to TinyLoRA, TinyLoRA can get away with as little as one single parameter being updated, whereas a full fine tune, you have NM dimensions of the matrices times the model width D, or like the size or length of your model. So this kind of it's intuitive, right? Because if you've ever done like a model merge or something, which is another sort of alchemy approach to joining fine-tuned models together, the merging itself usually targets pretty small subsets that are changed. So like that was the idea behind ties and DARE model merging, is there's some kind of cutoff. Like a lot of the parameter updates for a typical LoRA will just be noise, and there'll be a subset of parameters that have larger updates. And those are the ones that we actually want to pay attention to when doing any kind of weight merging. And that's sort of a similar insight they pull out in this paper, is that, we can really take a small subset of the model parameters for this specific task and update that scalar using reinforcement learning, this vector of scalar values where each scalar is multiplied by some random direction. And I think I failed to mention earlier that the randomly initialized matrices P are frozen during the update. So you're not updating the randomly initialized matrices. They just represent some random direction in your update space. The only thing you're updating is your scalar values V, which is just some vectors. So the RL process would be we generate a set of rollouts with our model. We score those rollouts with a reward function. And then we take a set of scalar values and we do gradient descent on those scalar values in this vector using the performance of, or the reward. So again, harkening back to the introduction, we don't need to pay attention to all these noisy tokens. The only thing we need to do is look at the performance of the model using its reward function, perform our updates, apply that adapter back to the model, do rollouts again, etc. So yeah, pretty neat little variant of LoRA. It would be interesting to see the comparison to other tasks. They focus on the math-related tasks here, primarily because math is a verifiable reward. There's just a verification function. You can check if the solution is right or wrong. It would be interesting to see if there's a way to adapt this to qualitative tasks. There was a paper that came out not too long ago. It's called I'm forgetting the name, is removing the verifier or something like that. They use inverse reinforcement learning to recover reward functions given fine-tuning data sets. So it'd be interesting to see if techniques like this can be extended to qualitative domains. But again, a pretty interesting research contribution. I will post the link to the paper on the description of this episode. And other than that, I appreciate you all listening. I hope you have a great rest of your week. Thanks.